Still sticking with indeterminate forms here. This video, we're going to talk about what happens when we have things on these bottom two rows right here, right? It gets a little bit more involved, but we're essentially going to turn it into 0 over 0 or infinity over infinity, and then kind of go from there, all right? So if we look at this first example, if I take infinity and plug it in for that first x, you get infinity. If you take infinity and plug it in for that bottom x, you get 1 over infinity, which is 0, and then tangent of 0 is 0. So this is indeterminate form, infinity times 0, okay? Which means you don't know what that answer is, all right? All right, now, what we can do here, you really don't want to mess with that tangent, all right? You don't want to drop that down to the bottom, make that a cotangent, especially if you got like an easy sign in there. You don't want to drop it down, make it a cosecant, forget all that, right? So I typically leave this harder looking part alone. And I take this x and I drop this down to the bottom. Now, when you drop it down to the bottom, you can't just drop a 5 down to the bottom and make it a 1/5, right? So when you drop it down to the bottom, you need to do the reciprocal of that. So think about it. If you divide fractions, that's still equivalent to the original problem, because when you divide by 1 over x, it's the same thing as multiplying it by an x over 1. Now, when you plug in the x's, so we already talked about when you go 1 over infinity, you get 0, tangent of 0 is going to be 0 on the top. And when you have 1 over infinity, when you plug in infinity on the bottom, you got 1 over infinity, which is also 0 on the bottom. So now that one step where you do the reciprocal thingy, that's what I'm going to call that technique, the reciprocal thingy. Drop it down to the bottom and do the reciprocal. Now you have created for yourself 0 over 0. Now we can use L'Hopital's rule like we did the other assignment. So when you do the tangent, you're going to do secant square of that angle times by the derivative of that angle. That angle is x to the -1, so multiply by the power, decrease power by 1. Down the bottom, you have another x to the -1, so do the derivative of that as well. Those cancel out, and you're left with that secant squared of 1 over x. And now when you plug in infinity right here, you got 1 over infinity, which is 0. Secant of 0 is 1 over cosine of 0 squared, which is equal to 1. So indeterminate form, think about it. If you were kind of told before, like infinity times anything should be infinity, and if you were kind of told before, like 0 times anything is 0, well, when we put those together, you know, worlds are colliding a little bit right there, right? So there's just weird stuff happens there. And I just want to mention too, if you, going back to like the very first day of the school year, if you graph this function, or if you made an XY chart, and you just plugged in larger and larger values for x, you want to decide, hey, what are my y values doing? Your y values are going to get closer and closer to 1. So we want to make sure we don't lose track of what a limit actually is. All right, so there's the reciprocal thingy technique. And then this one here, this next example, number 2, this one I think is easy to know what to do because you have two fractions, right? And if you have two fractions, chances are I'm just going to go ahead and get a common denominator and put those fractions together and get a single fraction, right? But let's talk about why this is an indeterminate form. Because when you take a 1 and plug it in for these x's, ln of 1 is 0. So you get a 1 over 0 and a 1 over 0. Now, remember what we said in the last video, that a number over 0 is a kind of infinity. So there are different degrees of infinity where you can't just say infinity minus infinity is equal to 0. This answer is not 0, okay? If you graph that function and you look to the right of 1, those y values are not approaching 0. It's just not true. So we can't go with our gut instinct whenever we're seeing this stuff right here. Now, so what I'm going to do, algebra technique, that's all we're going to do. We got to change it because I can't use L'Hopital's rule unless it's 0 over 0 or infinity over infinity. So all I'm going to do is create one single fraction, get a common denominator, one single fraction. That's all I did right here. And now when you plug in the 1, you get 1 minus 1, which is 0, minus ln of 1, which is 0. Ln of 1 is 0, 1 minus 1 is 0. You have 0 times 0. So you do have 0 over 0 now, which means I can apply L'Hopital's rule. So I have to do the derivative of the top. Derivative of that x is 1. The derivative of the ln of x is 1 over x. And then here, we need to do the product rule. So I did first times derivative of the second plus the second times the derivative of the first. And that's how I got this denominator here. Sometimes you could just plug in here. I like to get rid of my complex fraction. So I multiply the top and the bottom by the x to get rid of the complex fraction. And now when I plug into this step, you have 1 minus 1, which is 0 on the top. You have an ln of 1, which is 0. And then 1 minus 1 is 0. You still have 0 over 0. So it's still an indeterminate form, which means I don't know what the answer is just by looking at it. But I can apply L'Hopital's rule one more time. So do the derivative of the top, do the derivative of the bottom. When you do the derivative of this piece here, that is a product rule. So do the first times derivative of the second plus the second times derivative of the first. And then the derivative of that x right there is just going to be that 1. And then those cancel, those x's cancel out. So 1 plus 1 will give us a 2. And now you can take the 1 and plug that in right there. ln of 1 is 0. So we're going to get 1/2 for that answer. All right, now of all these indeterminate forms, it always kind of makes sense that something has to give, right? Like this one here, like if I have zero, you were kind of told before, like 0 to anything is just 0. And you're told before that anything to the 0 power is equal to 1. Well, when you put them together and have 0 to the 0 power, it makes sense that something has to give. We got to do some calculus in order to figure that out, and it will involve the limits, okay? What doesn't sit well with me is this whole 1 to the infinity, why that answer is not always equal to 1. But you got to remember we're doing limits. And so the limits we're getting like really, really close to 1 to the infinity, like 0.99999 to the infinity or 1.0001. So it's just different things of the graph. So if it's in that form, I just had to kind of work with the graphs and do some XY charts to kind of convince myself this problem, this number 3, this is in the form of 1 to the infinity. And if you graph that function and you look around 0, that answer is certainly not equal to 1. If you made an XY chart, if you made an XY chart and you plugged in for the X's, if you plugged in like 0.00001, those Y values are not approaching 1. So it just that's so I just kind of had to do normal stuff like that with the graph or an XY chart to convince myself that 1 to the infinity is truly indeterminate form. So when you plug in 0, e to the 0 is 1, 1 plus 1, 0 is 1, and then a number over 0 is infinity, so you have 1 to the infinity format. Now, whenever you have something that is on this bottom row, you have issues with the exponents. Last year, when you had equations to solve with variables in the exponents, you did the log of both sides. You did natural log of both sides to carry stuff down, right? And so you definitely want to use a natural log because it's easier to do derivatives with things with a natural log instead of like a different base, right? So here's what you're going to do. So it starts off like this. And what you're going to do is you're going to set it equal to y. And then your goal is to figure out what the y is equal to. So that's the first step I did in the green color right there. I set it equal to y. And then whenever you have that 1 to the infinity or 0 to the 0 or infinity to 0, anything on that bottom, on the bottom row, just the bottom row, that's when we're going to go ahead and, just take the natural log of both sides. Set it equal to y, take natural log of both sides. So I have the ln of y here. And then here, you're allowed to take that limit and write that limit notation first. And then you have the natural log of this expression right here. And then you're allowed to take that exponent and drop that down in front of that natural log. And so that's what I got going on right here. And then notice that I just basically just take this fraction bar and extended that, and I have a single fraction right now. And sometimes you're able to go to L'Hopital's rule right away. Sometimes what you create for yourself is something like this when you bring that stuff down and you got to do the reciprocal thingy. So this one here, I was lucky. I had one single fraction already. When I took a 0 and plugged it in for all those x's, I did get 0 on the top and the bottom. So then I did my L'Hopital's rule. I'm going to do the derivative of the bottom is just 1. The derivative of the top, that 2 just carries down, but now you have the ln of something. Remember, you do the derivative ln of something, you go 1 over that thing, times it by the derivative of that thing. So the derivative of e to the x was e to the x, and the derivative of that x, that was equal to 1 right there. And now if I take 0 and plug it in, e to the 0 is 1, 1 plus 1, I get 4 on the top. E to the 0 is 1, 1 plus 1, 1 plus 0, I'm going to get a 1 on the bottom. So I actually get a 4 for that. Now, a common mistake is students say that 4 is their answer on something like this. But remember, we set this original problem equal to y, and then we said we want to know what y is equal to, and then we did the natural log of both sides. So you don't have to write this down every single time, but you got to remember that that's what the ln of y was equal to, and then you use your main definition of log. Remember when you have, Ryan with my mouse here, it's a little bit janky, but when you have log base b of a equals c, remember our main definition of log is you can go b to the c is equal to a, right? And so that's what I'm doing right here. This is base e, so you can go e to the 4th is equal to y, and so e to the 4th is your answer. So even though it started off as 1 to infinity, that answer wasn't 1. And again, if you graph this function right here, or if you do an XY chart and you look around 0 from the right-hand side, your y values are approaching this 54.598 number, which is what that e to the 4th is right there. So be careful on that. That's a L'Hopital's rule with the different scenarios. And so if it occurs in this bottom row right here, it's probably, the second row, it's going to be like this one where you're going to get, you're going to get a common number, one single fraction, or it's going to be a reciprocal thingy. The good news is there's only 3 techniques, and all 3 of them will probably find their way in a testing situation right there. And once you know those few techniques, you're just going to be on the lookout for those, and you just know all of them. Now, it's important to know which of these indeterminate forms are on your list so that you know what's not on your list. So like this last example here is 0 to the infinity. 0 to the infinity, when I check, that's not on that list right there. So that means if it's not on the list, if you have infinity to the infinity or infinity times infinity, those are not indeterminate forms, which means you do know what the answer is. Those are your gut instinct answers. So if you think 0 to the infinity, I'm thinking that's just going to be equal to 0, and that's my answer. So if I have infinity times infinity, my gut instinct is just to say that answer is going to be infinity.